Hello everybody, in this one, just for fun, we're going to find the domain for this function here. Sine of tan inverse of x plus sine inverse of y. So first, so we can build up some pictures using triangles, we should know that where it says tan inverse, it's really x over 1 over here, and where it says sine inverse, it's really y over 1. You want to see that because those are ratios. And remember that the inverse sine, inverse tangent, they take a ratio and they give an angle back. So here I'm going to make use of that as follows. Based on this, I'm going to draw some triangles in here. Let me turn my grid on because it's easier to do that then neatly. So I'm going to have a triangle that looks like this. And then let's do one more. I'm going to need one more triangle. So I'm going to show you a way of doing this, finding a domain. Not the only way, but I like this way. I like math, so let's take a look. Here, because it says tan inverse of x over 1, what that says is the following. That this is essentially your x and this is your 1, which means by the Pythagorean theorem that for this first triangle the long side would be the square root of 1 plus x squared. And then over here for this one, because it says sine inverse of y over 1, that's like saying that this is y and this is 1, which means by the Pythagorean theorem that the bottom here would be 1 minus y squared. I'm skipping the step of showing the Pythagorean theorem. It's not too essential here. So now we can also label things. So this could be, for example, the angle beta, and over here this could be the angle alpha. I'm going to say the following, that alpha, down below here below the triangle, alpha equals tan inverse of x over 1, and then beta equals sine inverse of y over 1, which means over here back across the top I can make replacements. So where I see alpha, I'm going to use that to replace tan inverse. And where I see beta, I'm going to use that to replace sine inverse. So let's carry that out over here up across the top. I'm going to have sine, and instead of putting tan inverse, I'm going to put alpha plus beta, replacing sine inverse with beta. Now there's an identity for a sine of a sum of two angles. Let's write that identity down over here. So it's sine of the first one, I always have trouble remembering identities. Sine of the first one, cosine of the second one, plus cosine of the first one times the sine of the second one. And if you had a cosine here instead of a sine, if you had a cosine of a sum, then I think the sign in the middle in the expanded form is different. It becomes a negative between them. Roughly speaking, that's the idea. So sine of alpha, what that means in the shape is the following. It's x over the hypotenuse. So it's going to be x divided by 1 plus x squared. And you're going to multiply that by cosine beta. So cosine beta would give us basically the horizontal leg divided by 1. So that would be 1 minus y squared over 1. So that doesn't change anything. Plus, and then cosine alpha, well, that would be 1 over the square root of 1 plus x squared. So that would be 1 over 1 plus x squared. And then multiply by sine beta, which would be y over 1. Now when you look at this expression, let's zoom in on it. This contains only x's and y's, so it's good for finding the domain from first principles. In other words, we're not assuming any graphs, any familiarity with anything. We're just going to we'll just instead go by the simplest possible rules, remembering that we don't take roots of negative quantities, in this context at least. So specifically, take a look. This is x, that's fine. This is the root of 1 plus x squared. That's not a problem. For example, if you put in here x equals 0, it's going to be 1 plus 0 squared, which is 1. That's not a problem. If you put in x equals 1, it's 1 plus 1 squared, not a problem. If you put in x equals negative 1, it would be negative 1 squared, which is 1. 1 plus 1 is 2, not a problem. So because that 2 is present in this exponent, it makes any input in here either 0 or positive. So that means under the root symbol, you always have an expression that is essentially positive because there's also this 1 present here. You see that? Like if x is 0, then 1 plus x squared is 1 plus 0, which is 1. Any other value of x you input in here would be, say, x equals 5. That would be 1 plus 5 squared. That would give you 26. So it's always more than 1, basically. Not a problem here. Same thing applies over here, but there's a problem in this location. So for that reason, you have to look at some potential problems here. Imagine that y has the value 2. So if I plug that in here into the root, I'm going to have 1 minus 2 squared, which is the root of 1 minus 4, which is negative 3, which is then the root of 3i. That's a problem because that's not a real valued quantity. It's a complex number. And remember that in all of this, because it's coming from triangles, this part by itself, take a look, right here. That represents this leg of the triangle, so it's got to be 0 or more. That can't be a complex number because I don't know what a complex number side is for a triangle. So these kinds of considerations are suggesting that to find the domain, you can write down this on x. So negative infinity is less than x, which is less than positive infinity. For the second one that involves y, you have to be more careful. The domain has to be such that this expression right here, under the root symbol, is always 0 or more. So I can take the square root as a real number. So let's work that out. I'm going to have 1 minus y squared has to be greater than or equal to 0. That's our goal here. So I'm going to factor 1 minus y, 1 plus y. It's a difference of squares pattern, greater than or equal to 0. Then you set each one equal to 0 and you solve. So 1 minus y is 0. Then another one is y plus y is equal to 0. Let me zoom in on this work exclusively here. So from the first one here, I'm going to have y equals, subtract 1, but then divide by 1 negative again. So y equals positive 1. For the other one, y equals negative 1. Let's put these on a number line. There you go. Have a nice double-ended arrow. And let's mark these. So say this is now negative 1 and this is positive 1. Those values are included because in our inequality we have the greater than or equal to parts. So because of this portion here, I'm going to put solid dots. Let's choose a test value. That's the next step. So imagine the simplest thing, 0 between them, and plug that into the inequality. You can tell very likely just by looking that it makes the inequality true, but I'm going to test it over here. So plugging in this test value, I'm going to have 1 minus, and remember this is the y-axis here, so 1 minus 0 squared. Is that greater than or equal to 0? Well, let's see, that's 1 greater than or equal to 0. Clearly that's a big check mark right here. That's true. So that's telling us that the correct portion to be shaded is this one right here. That's the domain on y, from negative 1 to positive 1. As an extra, what you may want to consider next is understanding what all of this actually means in terms of the triangle. So here's an example of what I mean. Imagine that y has the value 1. What happens to the triangle in that case? Because it's coming from a triangle here. Well, in that case, it's the hypotenuse, so that never changes. It's always equal to 1. But then the vertical leg, y, has to be equal to that same value, so it has to overlap with it, like that. So this is also now y equals 1, and this is hypotenuse equals 1. And then the question is, what happens to the horizontal leg? I'm going to kind of just suggest it with barely a dot. Well, that would be equal to the following. Work it out. It would be square root of 1 minus 1 squared, which is 1 minus 1, which is 0 once you take square roots. So in that case, this is equal to 0. I've shown you the case that applies when y has the value positive 1. What you may want to do is repeat this for yourself when y has the value negative 1. How would the triangle look? What would be the value of the so-called horizontal leg in this context? And so on. Those are little things that you can do on your own to extend what we've done in the lesson here. Now let's summarize our findings by making a picture of the domain. So the domain, this is going to be our y-axis. This is going to be our x-axis here. For the y, let's label everything. So this is going to be the y and this is going to be the x. Remember that our function here is a function of two variables. So x is one variable, y is the other variable. So the picture of the domain is a picture of the xy plane, a shaded region within the plane. So here, I'm going to proceed as follows. I'm going to say that the values of x can be anything, but the values of y have to go between negative 1 and positive 1. So over here, I'm going to mark this line. And this represents, for example, y equals positive 1. Let's also mark one down below. 4 spaces, say 1, 2, 3, 4. So this represents the fact that y equals negative 1. And because there are no restrictions on x, remember that x is this quantity, this is the domain, just by observing that over here in this triangle x can be any value. In other words, as you can see, because you have only x and 1 plus x squared under the root symbol, x can be any value whatsoever. There are no restrictions. So over here, what I'm going to say is the following, that x can go towards negative infinity, and x can also go towards positive infinity. The domain would be all of this. Any value that you choose from here any point, any combination of x and y, so for example like a random dot, like that would be okay. But on the other hand, if you choose a value out here, well, clearly that would not be okay. So let me zoom out. I've zoomed out here in all of our work. Thanks so much for watching. I'll see you in another video.